Good afternoon. This is the first of a two presentation set on multiples. The first presentation here is about why do we need to remove multiples in direct seismic methods and indirect seismic methods. Multiple removal has been a long-term objective in seismic exploration. Recent methods that use multiples for different processing goals and objectives can be worthwhile. However, their use can also be a source of confusion as to whether the removal is no longer essential, a priority, or even necessary, since some may now view multiples as rehabilitated and sit alongside primaries as entirely useful events. So we recognize that primaries are useful. If multiples are useful, why do you want to remove multiples? That's a reasonable question. Why are you wanting to remove seismic data that's useful? So one purpose of this presentation is to disabuse us of that seriously flawed and erroneous thinking, and to understand that the use of multiples, for example for imaging, and the removal of multiples have the same exact goal and objective. That objective is the imaging of primaries. Furthermore, we explain why multiples need to be removed in all direct and indirect seismic processing methods, and therefore why multiple removal remains a key and central issue and challenge in seismic exploration. Furthermore, every method that uses multiples today, for example, using multiples to find an approximate image of an unrecorded primary, or using multiples in model matching methods like FWI. Every one of these methods that uses multiples, at the end of the day, make the removal of multiples even more significant. That's a very important message. Rather than making the removal of multiples less significant, each of them, we will show, within their own application, require a heightened interest in the removal of multiples. So the usage heightens the need to remove. So these are not well understood ideas. The use and removal are often viewed as adversarial. And what we're saying is they're not. They're in fact aligned. So we will show in this presentation how all direct and indirect seismic processing methods remove multiples at some step or stage within the method. All, that means without any exception, every seismic method today, whether it's a direct method, with a velocity, without a velocity, indirect method, using some criteria that you assume an image would satisfy, and applying that criteria, driving a method towards that criteria satisfaction. Model matching methods, where you're model matching primaries and multiples of different varieties, that every one of these methods within the method itself, either initially or eventually, has to remove multiples. So there are papers that we've published on this topic, and this is just a sample from a paper in the journal Interpretation, and another paper from the Ecopatrol's journal in Colombia, the country of Colombia, among others. So again, we can view this presentation as a two-part, part one of a two-part set. This part is, why do you need to remove multiples? What exactly is the issue? Yes? And the second is, okay, assuming that this first presentation convinces you of the essential nature and priority, heightened priority of removing multiples, then what is our current state of multiple removal? How has multiple removal methods, how have they evolved? What's the current toolbox of capability, and what are open issues yet to be addressed? So as I said, for the purpose of this presentation, there are so many seismic methods. So it's useful to have catalogs to try to separate, and then within the catalog to see how multiples are, what is the issue with multiples. So we're going to first separate seismic methods as being direct or indirect. And we're not going to go through in this talk the meaning of direct, other than to say if you have the quadratic equation, ax squared plus bx plus c is 0, and you have the solution, minus b plus or minus, that's direct solution. You give me a, b, c, I have a formula that directly provides the roots. An indirect solution to that would be, let's guess. Let's guess. Let's look at error surfaces of ax squared plus bx plus c and look for a minima, a global minima. That kind of would be a prototype indirect method. And as I say, we've published extensively on that difference, and that difference is something that's worth for our students in this audience to have a clear understanding of that differentiation. That doesn't mean that one is innately superior and is always the method of choice, as we have published. And we believe direct methods should be used where you have a description of the physics, the seismic physics. What do you mean by that you have? You have a model for what the seismic physics is. For that physics statement, we advocate using direct methods. But no seismic model is going to capture the reality of the real world, the real seismic data, the earth, the near surface, the complexity. So there's a part of what we're collecting there's always beyond whatever the physics model is. And for that part of your data that we understand is beyond our assumed physics, not beyond a physics, but what we're assuming to be the physics. There's a physics. How do we know there's a physics? Because when that source goes off and that wave goes in the earth, it doesn't come and ask us where to go. So something is, there's some physics mechanism that arranges for the transmission reflection of that wave without the need for us to tell it what to do. Yes. So there's a physics. There's a difference between the physics there and our assumed physics, and that difference is where indirect methods, in my view, needs to apply, because there's no choice. It's beyond your partial differential equations. It's in your data, and it would be prudent to have some accommodation for that beyond your physical model of components of your data. And that's where statistics and all other indirect methods, in our view, have a role. And it's the combination of direct and indirect that we need to keep an eye on. Frankly, the indirect has become all the fashion. Computers, searching, machine learning, AI, it all drives you away from thinking. AI, what about actual intelligence? The quadratic equation, that solution, okay? That's not machine learning, okay? That's real intelligence, okay? Okay, so the direct and indirect, and we've published extensively on those differences and the strengths and limitations of each. So we're going to start with seismic direct methods which require a velocity. In other words, to apply the method, you need to have an adequate velocity model of the Earth between your source and receiver measurements and where you're trying to locate hydrocarbon. You have to have some information in those direct methods which require a velocity model. And the method that we're, of course, having in mind is the method or methods that are seeking to find structure, boundaries, where are rapid changes of Earth material properties occurring. And that method is migration. And the methods that use the wave equation for migration have two ingredients: a wave propagation component and an imaging condition. Two components. A good place to start a study of migration, which is important from our perspective, is to go at the right place upstream. Migration did not start with RTM. There are people who start studying migration as though, let's write down the RTM formula. It's like Kleenex and tissue. RTM is a form of migration. It's not where migration started, and it's a terrible missed opportunity to believe that that downstream and important method is the origin of the thinking. A good place, in our view, to start thinking about migration, and in particular, the one ingredient that we call the imaging condition, is John Claerbout's landmark paper in 1971, where he lists three imaging conditions. Imaging conditions, one is the exploding reflector model, which is for stacked data. The second is the time and space coincidence of downgoing and upgoing waves. In other words, you take the upgoing wave that you've recorded and take it down in space. They were talking about one-way waves then. You take the source wave field, and you generate from what that source is, what is its wave field going in the Earth. And you look for the time and space coincidence of this wave from the source down and the reflection data back. Where are they time and space coincident? And that idea is you will locate a reflector where the down and the up are at the same place at the same time. So that's what imaging condition 2 is. Imaging condition 3 is very different. It says, from your actual sources and receivers on the Earth's surface, can you predict, given a velocity model down to some depth, what a source and receiver experiment would do in the subsurface? In other words, from actual sources and receivers, predict what a source and receiver would record if the source was in the Earth and the receiver was in the Earth and they were coincident, and then ask for t equals 0. In order to get receivers, from receivers on the Earth's surface, a predicted receiver in the subsurface, you need a form of Green's theorem, for example, to make that prediction. You need receivers for a given source to predict for what that same source is, what a receiver would be inside that medium from the surface receivers. Similarly, if you now want to find out what the source would be inside that medium, you need a collection of sources. So the idea of predicting what a source and receiver experiment is in the subsurface is very different. This 3 is much different. If you say the words, they might sound similar. But one is taking the field. 2 is taking the field from the source down. This 3 is taking the source in. Okay? That difference cannot be overstated, the significance of that difference. The third is predicting an experiment. And then it says, if you have a coincident source receiver at a given position in the Earth, and you happen to be above a reflector, and ask for t equals 0, then if you get a non-zero result, that coincident source receiver is the location of a reflector, period. If that source and receiver at some location in the Earth at t equals 0 gets 0 as a result, because the reflector is not located where the source and receiver is, you'll get, for time equals 0, you'll get a 0 result. Then at that coincident source and receiver position, there is no reflector, okay? So we'll see how this all plays out. So a very important point in this lecture is that all current seismic methods make high-frequency approximations in either the imaging principle and or the propagation model. So let's focus on the imaging principle. In other words, let's focus on what we just said, where we're going to look at the pre-stack case only, so we're going to exclude the exploding reflector model, which is only for stack data. So we're going to look at the time-space coincidence of up and down going waves and the third. Compare these two. This time and space coincidence of up and down going waves was originally, for John Claerbout, for one-way waves. So it was back in depth and forward propagate that field from the source in depth. Yes? That evolved to back propagate in time. The same imaging principle evolved by Whitmore and others to become RTM, but it's the same imaging principle. The original was back in and forward in depth. Whitmore and colleagues advanced that to back in time. That's where the word reverse time migration comes from, yes? Going back in time. But reverse time migration is imaging condition 2, yes? So what we're going to do is, let's take the simplest problem in the world, a homogeneous medium, a single horizontal reflector, take one source, one receiver, and then look at what these two imaging principles, where it's homogeneous above. We use analytic data. We implement the imaging conditions analytically, okay? And you get the following. You get these three results. This is RTM, imaging condition 2. For one source, in other words, you have one trace, one source, one receiver, yes? You have a horizontal reflector. You take that trace and you apply the RTM imaging condition, and you get a travel time curve. Okay? If you take an asymptotic approximation to imaging condition 3, in other words, you take, for example, Fourier migration, Stolt migration, and you do a high-frequency approximation to that form of imaging condition 3, you will get a Kirchhoff migration. Very similar, travel time, yes? If you take imaging condition 3, yes, you get this. You do not get a travel time curve. You get something trying to approximate a point, yes? It doesn't have the wherewithal with one trace. The point is, a very important point here is, RTM is a high-frequency approximation, just like Kirchhoff. How do you know? Well, what does this curve mean? This curve says this, for one trace, you get one event. That event is placed on a travel time curve. That curve is ray theory, saying this gives you the time. That is a ray theory thought. That's not wave theory. So RTM and Kirchhoff do not tell you unambiguously at a point that you do or do not have a reflector. What they each do, is they give you, for one event, they get placed on a candidate of possible reflectors. And then when you take the other traces and other shots, what you're looking for is constructive interference of these possibilities, yes? You look for constructive interference. That's a high-frequency ray thought, okay? And there's no way that any application of 2. No matter how you implement it, in depth, in time, least squared RTM, it is this picture, because that's the imaging condition. You might have some propagation model. That's another issue that we'll address in a minute, okay? The imaging condition itself, with perfect data where there's no propagation issue, gives you this. So why does that matter? We have Professor Meyer here and Anna here. If you have a migration method, and we'll say more about this later, that's a high-frequency approximation. High-frequency approximation means it's a better approximation the higher the frequency. So if you get more low frequency, yes, it would rather have more high frequency, okay, because it's more accurate. So this whole study came about because one of our sponsors in the Middle East told us they're very interested in acquiring more low frequency data. When they did, at great expense, they found advantage over the non-extended bandwidth data. They found advantage, but they didn't see the same advantage as the data seemed to have. Something about the migration discounted the value. If you looked at an arrival with the original data and you looked at the arrival, just the arrival, with the band extended data, you could see a significant difference because it has more low frequency. When you looked at the migration result for each of those, there was a difference, but not what they hope for imaging, getting structure and amplitude analysis. Something about the migration was not treating the low frequency. So that got us all interested. That's why we got involved in it, to take a look. So sure enough, the methods that are considered, you say migration, they say RTM. This is what you have. And there's, we'll mention this, we looked at the relationship between Claerbout 3 and RTM for resolution, for example. And for the same bandwidth and an analytic application, RTM for a certain distance between two reflectors thought it was a single reflector, and this imaging condition 3 saw it as 2. So this would see a reservoir and this would not. So as always, the acquisition advances and processing have to cooperate. So as I said, we're going to treat these, we're going to call these Claerbout 1, 2, 3, and so the third imaging condition, for a set of reasons, stands alone. The prediction of a source and receiver experiment at depth, the physical meaning of it. First of all, there are no candidates in Claerbout 3. FK migration doesn't give you candidates. You predict a source and receiver somewhere. FK migration is a Fourier implementation of Claerbout 3. And in FK migration, you don't get travel time curves. You predict a source and receiver at a given point in the Earth. You ask for t equals 0. If you get a non-zero result, there's a reflector there. Okay? It's not a possible reflector. Okay? So once you have that, the ability to do amplitude analysis is so much greater. It can be extended into imaging, curve, dipping, diffractive boundaries with subsequent amplitude analysis because of the sort of constructive interference nature of RTM. So it's been limited, RTM, in its extension to specular reflection and an asymptotic approximation to specular reflection. It cannot be generalized as Claerbout 3 can to curved, pinch-out imaging without a problem, because you're just predicting at that point, is there or isn't there? You're not looking for constructive interference. That's not a well-known point, okay? It's such a group thing, okay? Lockstep RTM. Again, RTM is not the problem. RTM is a method. Methods don't have egos. Methods don't have ambition. Methods don't have integrity or lack of integrity. People, okay? We have to, when I've said some things of concern for different methods, I'm not talking about the methods. I'm talking about people who overstate capability, do marketing, or say their methods have no assumptions. There is no method that has no assumptions. As soon as someone says their method has no assumptions, they're not talking science. Whatever they're talking, it's not science, okay? As soon as you write an equation down, okay, you do imaging. There's a whole set of prerequisites. You have to get the reference wave out, you have to do deghosting, you have to get multiples out. Those are all steps, no matter what the imaging method is, okay? If you start to hear, we have no assumptions, you should just get like a red light that whatever you're listening to, and that doesn't have anything to do with how many degrees you have. The issue of integrity is that somehow you either have it or you don't. Okay. Again, RTM is not a problem. RTM has value. If people are just saying that is the only thing we can think about, that is the issue, not the method. Okay. So there's extensive work, Stolt and colleagues extended Claerbout 3 to do amplitude analysis, for, an automatic amplitude analysis. In other words, determine a structure independent of its complexity, and to do subsequent amplitude analysis at that located structure. This, it turns out, is not just important on its own as an imaging method, but within multiple attenuation removal methods reside imaging algorithms, okay? And the capability of different multiple removal methods, as we'll mention in the second talk, the capability comes back to what imaging condition they're using. Because if you're treating something within your multiple attenuation method that has an ingredient which is Kirchhoff or RTM, then you can deal with a complex generator of the multiples because its imaging is restricted. If you have a Stolt Claerbout 3 imaging within your multiple method, then the generator of the multiples that it can accommodate is general, okay? Arbitrary geometry. So it's these, examining these imaging conditions are important on their own. They're also important in when they reside within multiple removal methods, that they have consequences for the effectiveness, okay, of the ability to predict and remove. Okay, so our group, MOSRP, in the last several years has extended Claerbout 3 to deal with non-homogeneous medium. So let's go back to this high frequency story. How do you know if a migration method has a high frequency assumption? How do you know? One is if there's a travel time curve. If there's a travel time curve, you know right away that the travel time curve is ray theory. So the time of that arrival could be somewhere on an ellipse. That's not wave theory, okay? So that's one. If the imaging condition has a travel time picture somewhere within its development, you are dealing with a high frequency approximation. That imaging condition is making a high frequency approximation, which then will affect that migration no matter what the propagation model is, okay? Now the propagation model itself can have issues. In other words, how we assume waves propagate in the medium. So, and that can affect, and has affect, and does affect implementation of Claerbout 3, not just 2. So let me be clear. If you you have a point in the Earth, and a wave comes down to this point. And if I assume at that point that the wave which is coming down leaves that point going down, the only time that's true is if that point is in a homogeneous medium. In other words, a wave traveling in a homogeneous medium goes in one direction. As soon as there's any deviation from homogeneous, it could be smooth, yes? Doesn't have to be discontinuous, which of course will make two-way. But if it's smooth, and I assume that at some point that wave arrives through the smooth medium, and at that point it's going down only, that's a high frequency approximation. Of course, for any heterogeneous medium, part goes down, part goes up. That is called, that one-way assumption in the propagation model is called WKBJ. Okay? Again, that's a high frequency approximation. And we'll see. So our interest in avoiding high frequency approximations early on, several years ago, was to get the benefit of low frequency data. Yes? So if you're trying to get the benefit of low frequency data, make sure your imaging condition and your propagation model don't make high frequency approximations. So what MOSRP contributed was on the propagation model. Yes? The imaging condition was there with Stoltz, myself, and others. Yes? And that was extended to do amplitude analysis before we arrived in MOSRP with that. What we did is arrange for the propagation model to accommodate discontinuous velocity, which is definitely going to be two-way, discontinuous velocity above the target. There are people who say, oh, migration is just circular reasoning. To do migration, you need the velocity. If I have the velocity, I don't need to migrate. That's a little too quick. Migration doesn't assume you know the velocity. It assumes you know the velocity adequate to find the structure. You don't need the velocity below. Okay? And it can be smooth as long as it well locates. Yes? Now, if you assume it's smooth, what we're saying is don't make a high frequency approximation in the smooth down to this, because the high frequency approximation will again discount low frequency components. Yes? So on both the imaging component and the propagation component, if you're interested in equal effectiveness at all frequency, avoid high frequency approximations. And so two things were accomplished. There was an extension of Stoll-Claerbout 3 to heterogeneous media, both smooth and discontinuous, without having that propagation model making a high frequency approximation. Okay? So this showed a paper by Yang Li Zhou et al. 2017, SEG, showed the difference in resolution between this Stoll-Claerbout 3 and RTM of the variety I mentioned earlier in terms of being able and not being able to resolve a reservoir, yes? And how they, both conventional and broadband data. In other words, the comparison was, now we give you more low frequency. How does each benefit from the added low frequency? RTM benefits, but not as much as Stoltz C3, because Stoltz C3 doesn't make a high frequency approximation. Yes? So we're going to avoid, we want to accommodate accommodate discontinuous velocity models. We'll say avoid high frequency. One way, this was the original driver to avoid high frequency approximations. The accommodation of discontinuous velocity models allows your migration to accommodate multiples. In other words, if you're serious about predicting a source and receiver at depth and are really interested in that experiment, you have, and you want to analyze the role of primaries and multiples, you have to have a model that understands where multiples came from, yes? So you have to have, allow a discontinuous velocity model. RTM, let's just say directly, RTM cannot accommodate a discontinuous velocity model, cannot. You can't get through one reflector with the velocity. Yeah? You can't image beneath. And there's well known, it's the imaging condition. It has nothing to do with the medium above that reflector. It's the imaging condition that falls apart. You get rabbit ears, all kinds of artifacts. Just taking a single reflector and take RTM and try to image beneath it. You're going to get all these artifacts. Yes? Now people, Facci Liu, Scott Morton, Jacques Levet, have come up with methods to remove those artifacts. Yes? And Facci Liu received a well-deserved honor from the SEG for that work. Nevertheless, that removal of the artifacts damages the image. Okay? And that's a downside. This is the formula, the migration formula for imaging with Stoll-Claerbout 3, in other words, the third imaging principle, where for a continuous or discontinuous velocity, yes, this formula will be the formula that will not produce artifacts. Okay? You'll see the result in a second. So this is Claerbout 3, if you like, how you image through a smooth velocity without making a high frequency approximation, or how you image through a discontinuous without any artifacts. You just predict the source and receiver. There's no artifacts. You just have an experiment predicted. So that's a two-step procedure. First you bring the receivers down with the source on top, and then you apply on the predicted receiver at depth with the source on top. Then you take that experiment and apply Green's theorem again with a Green's function that satisfies the smooth or discontinuous velocity model with Dirichlet and Neumann conditions both beneath where you're trying to image. That's what that G0DN, and we refer you to literature on this. Okay. So this is with the source and receiver at depth, where the inside data has the receivers down, but not yet the sources. And then you integrate over source. Okay, so this is important. They say that's wonderful. What does it do? This is the work of Chung Fu et al. This is a single reflector, yes? And it's imaging above, meaning predicting a source receiver above, no big deal. That's homogeneous, yes? It predicts it below, yes? In other words, one is dark, one is light, and one is dark because they have opposite reflection coefficient, light and dark, yes? And there's no artifacts. In other words, there are no rabbit ears to remove, okay? You're predicting an experiment, that's all. In other words, the Claerbout 3, it's physical interpretation. It's not ad hoc, okay? Claerbout 2 is somewhat ad hoc. You take, in principle, very important, in principle, Claerbout 2 says, for one shot record, take the data back. Okay, take it, just reverse time it. And for one shot, take the field from that shot and forward propagate it. And look for the time-space coincidence. In principle, that is supposed to give you a reflector. But it doesn't. It gives you, for a single reflector, something which laterally varies, which doesn't make sense. It's two homogeneous half spaces. So they say, well, let's do that for many shots and sum them. That's not a method. There's something that's not physical in the method. In other words, let's just stack things that are wrong and hope they fix themselves up, okay? That's what RTM is. That's what it is. Claerbout 3 is not that, okay? It says you need all receivers to get one receiver down, all sources to get the other. You're not summing over sources to deal with an artifact, okay? You need to do a Green's theorem sum over sources to predict that source, okay? It's not a fix, it's a method. Okay, so this is Chung Fu al. Now, this is a paper that discusses the resolution benefits. Okay, so we have this Claerbout 3 migration. Well, it's in this paper. Okay. You have this form, yes? And what we're going to do is we're going to use it to image through discontinuities, yes? We'll have a set of layers, and we're going to take primaries and multiples, okay? With this formula, yes? Discontinuous velocity, assumed to be perfect, and predict the source and receiver with primaries and multiples above and below each reflector, with free surface multiples and then internal multiples to see what happens. Because this can accommodate a discontinuous velocity. So migrate in it and see what happens to primaries and multiples. But we're about to say you cannot do with RTM. It cannot accommodate discontinuity. Okay? If you have something with rabbit ears, yes, you're not accommodating. There's something in the imaging condition that's troubled when you go beyond a reflector. Okay? Okay, so this is a very important key point. And we're going to show you a cartoon of what there is an analytic work with that formula that Stoltz C3 extended to discontinuous media. Yes, that formula. We're saying, let's look at this is a primary, and this is a free surface multiple. And let's just see what happens. So this is the actual source and receiver. Now let's look what happens when that source and receiver are predicted at, let's say, right above that reflector. Yes? When you do, you can see on this picture, this guy is going to become this. And this multiple will become, for source and receiver like that, will become that. Yes? That's what you see here. Yes? And now if I say, for that source and receiver above that reflector, ask for t equals 0. This one will contribute and this one will not. Means if I had this velocity above and I made a quiescent, the quiescent source receiver experiment cares about all the data. In other words, this experiment cares about the original primary and the free surface multiple. But when you ask for t equals 0, only the primary contributes. The multiple doesn't contribute. It doesn't hurt. It doesn't help. Underneath, the original free surface multiple actually looks like a primary from the top. Okay? And the primary itself looks like a primary from beneath. So when you ask for t equals 0, the multiple, which you can, in other words, the multiple is like this. As you bring it down, yes, it starts to lose these legs, and you're getting this. And then the multiple, when you go underneath, yes, is just, yes? Understand? It becomes in its own data, the original multiple becomes a primary from the free surface. But its time is, at time equals 0, this is not going to contribute. So when you're underneath, the original, so if you had the velocity here and used Stoltz C3, not RTM, RTM would give you some ears here, you understand? If you did this. Here there's no ears. What you get here is minus R1. That's what you saw in Chung Fu's case of light, dark. He went underneath. Okay, so let's continue. Now, what this is showing is internal multiple, yes? So, here you have this black line is a primary, yes? The red line is a primary, and the blue line is an internal multiple, yes? Let's just watch what happens as that experiment moves into the Earth, yes? Is it clear? Because that's what the source receiver prediction is doing. When the source and receiver are above this reflector, you can see that the deeper primary is this, the internal multiple is this, and the primary that was originally just this is here. When I ask for t equals 0 for this experiment, only the red lives. The multiples, they're not arriving at t equals 0. But now here you have C0, C1, and I'm imaging above this, I'm imaging above the second, yes? So above the second, the original primary, this primary became, that primary became this. In other words, a primary like that, if you drag it down, in other words, it was this, down this, this. So you see the red line here is what that original primary from the first reflector became. Yes? The internal multiple that became the blue. And the black is the primary from the second. Yes? So if you now ask, this experiment predicted source and receiver above the second reflector and ask for t equals 0, you get this. The multiples are gone. What do you have to have this happen? You have to have an accurate discontinuous velocity. If you had an accurate discontinuous velocity and you use Claerbout 3, okay, extended to discontinuous media, then multiples will not cause a problem. You could ignore it. Just put primaries and multiples in. They're not going to cause an artifact. They cause an artifact if you give me a smooth velocity. And this is the real. Because then, for the smooth velocity, every event is going to be placed somewhere. And every multiple will cause an artifact. So the reason that multiples are an issue in imaging is our inability to find an accurate discontinuous velocity. So even if you had an accurate discontinuous velocity and you use RTM, it's not, that method is going to have problems at the first reflector. You have to use a method that is an extension of Claerbout 3 with a discontinuous velocity, and then multiples would have no problem. If at some point in the history of seismic we come to a state, which we are not in now, where we can predict an accurate discontinuous velocity, then you can shut down all your multiple removal methods. Okay? Use Claerbout 3, and multiples are not going to help or hinder. So for imaging with the most capable migration method, the smooth velocity is why multiples have to come out. Again, this shows going under the second. Yes, under the second reflector. Yes, again, only the second primary at time equals 0. The experiment under the second cares about all the events. Yes, you see red, blue, yes, all of them, but at the both primaries and the internal multiple originally are in this new data. But once you ask for t equals 0, then only that second primary contributes. Okay. So this looks like cartoons there's a paper by Fang Lu and myself that entered a interpretation paper, the math details behind this. So the math detail is not cartoon. The cartoon is telling you what happens, but gives you some reasonableness. Okay, so for a smooth velocity model, multiples will produce the industry standard smooth migration velocity drives the need to remove multiples. Okay? Okay, so that's the state of seismic processing, direct method with a velocity, yes? The only method that we know of, or set of methods, that is able to do seismic processing directly without any subsurface information. Doesn't mean they don't have any assumptions, but subsurface information is not one of them, yes? There are a set of procedures that have to come before multiple removal, deghosting and all. So, but the only method that doesn't require subsurface set of methods comes from the inverse scattering series. And okay, so and the inverse scattering series, we might as well say it. It has subseries that remove multiples. If they needed the multiples to do their imaging, amplitude analysis, Q compensation, they wouldn't have the capability to remove it. It's a direct method. They have a machine whose entire purpose is the removal of one or another type of multiple inside this direct machine. You can't make that machine do that. The machine has an apparatus, yes, within its procedures to achieve that. Its attitude, the inverse scattering series attitude to multiples is they are a form of coherent noise. That's its attitude. It's mathematics. It's not fashion, okay? You write the inverse scattering series and you'll see terms whose purpose is removal of multiples, yes? That's interesting. Because when we went into that, we thought, well, we want to remove multiples. Who knows how the inverse scattering series, maybe they're going to want to use them, you know? They don't. If they wanted to use them, they wouldn't have a machine to remove them. They don't remove things they want to use, okay? So let's go to a direct method that uses multiples. In other words, we're looking at direct methods that need a velocity, okay? We said we started off, we're going to look at all seismic methods as direct and indirect. Then with indirect, there are methods that require a velocity, and then there is this inverse scattering series that do not, okay? We just said that the inverse scattering series says unambiguously we want to remove multiples. We don't need multiples to accomplish depth imaging, amplitude analysis, and the rest, because it's built in, a removal apparatus. It's never using a multiple for imaging, okay? So that's, but let's talk about a use of multiples, a direct use of multiples, yes? So it's a direct method, it needs a velocity, and it's using multiples for the following purpose. First, only primaries are migrated. There's a statement. What do you mean only primaries are migrated? The thought, the concept of a multiple being migrated has no meaning. When they first started using multiples, they said they were migrating, and I kept repeating, you're not migrating a multiple. You're using a multiple, okay? So we'll clarify what that means. Go back to the original idea of what migration is. You have an event on a trace. So there's a receiver and there's an event on a trace. You want to know, is there a point on some reflector where a reflection, yes, is responsible for that event? A reflection is responsible for that event. That's what migration's about. You can formulate imaging conditions, and that's what it's about, a map between time of an event and the location on a reflector, yes? So that thought has no meaning for a multiple. I'm going to have a multiple, and I'm going to map to what? All the reflectors that contributed. The thought of migration, the thought behind migration is about primaries. Okay? You understand? So that has changed. You see now, instead of people migrating multiple, they're using. So I'm happy to see that. Okay? PGS, a leader of the method, says using, yes, rather than migrate. There's several reasons. If you're migrating multiples, going back to the migrate primaries, migrate multiples, why get rid of multiples? Yes? We'll see why you have to get rid of multiples. So there's two types of primaries, okay? Those that you've recorded and those you haven't recorded, yes? That's a way to classify. Multiples can be used at times to provide an approximate image of an unrecorded primary. In other words, there are primaries that, in other words, you have a source and receiver, and there's a single upward reflection, but you don't have a receiver there. So it's unrecorded. Or there's a bounce like this, and you didn't have a shot here, yes? In other words, either or both would give you a missing primary, yes? So you can use a multiple at times to get an approximate image of an unrecorded primary, and it's a direct method, okay? Meaning that method works, you give me a velocity, yes? I will get an approximate image, yes? It's not searching or matching, yes? Migration is a direct method with a velocity, yes? There's a formula. Out comes the image, okay? Okay, so you can have direct methods with or without a velocity. So in the evolution of seismic processing, methods, acquisition has become more and more complete. There was a time when we only had 2D data and we'd use asymptotic methods to approximate an experiment that had no cross-line data, yes? Ignoring the actual data that was there. That has changed. Single component onshore acquisition was the rigor, now not always. Single cable methods to do wave separation and deghosting has evolved to dual cable and so on, yes? Going to broadband, yes? Advances in acquisition, yes? So initially, the limited acquisition, which we always have, we try to accommodate with processing. Sometimes advances in processing will require advances in acquisition, and you have to justify each by what's the value. It's easy to say, but what actual improvement in drill prediction will an added cost on acquisition or processing require? Okay, this is sort of summarizing what we said. For a correct discontinuous migration velocity with a C3 imaging, multiples will not cause false images and will not be harmful or helpful. Okay. So this is using a multiple, yes? Using a multiple to get an approximate image of an unrecorded primary. This is a direct method, and it requires a migration velocity, yes? So it falls within what we're still covering, direct methods. This is a use of recorded multiple, yes? So assume this is a recorded multiple, and assume that this event, P1, is also recorded, yes? And somehow you take this recorded multiple and this partially deghosted primary, and you use those two in combination to get an approximate image of P2, this assumed unrecorded primary, okay? So there's a procedure, and it requires an RTM form of migration. It has not been extended to C3 using a multiple. So what are the requirements here? The requirements is you have a recorded multiple. The second requirement is the recorded multiple has subevents, yes? One of which is recorded and one is not recorded, yes? So, and then you use this in combination. In other words, this is recorded and this is recorded to get an approximate image of what primary P2 would give you if it was recorded, yes? It's an attempt to fill in, yes? Yes. So how this happens, there are references. And Nizar Chimingui of PGS has pioneered this, okay? And to good advantage. But what if you, so this is what is assumed. What if you had a multiple like this, yes? And you had this recorded, and this recorded, and this was the other event. The other event was a multiple. And you treated it as though it was an unrecorded primary. Then you will have a false image. You will migrated a multiple with a smooth velocity, which is what, again, it always goes back to that. And with a smooth velocity, an imaged multiple will give you an artifact. So, what we've shown before is for a smooth velocity model, if you have recorded primaries and recorded multiples must be removed, or they'll give artifacts. Yes? That was established previously. What this is saying is if you have an unrecorded primary that you're trying to find an approximate image of, yes, using this in combination with this, then you have to assure that this unrecorded event that you have is in fact a primary. So if there are unrecorded multiples there, that unrecorded multiple must be removed. It will give you an artifact if I treat it as though it was a primary. So to image with a smooth velocity, to image primaries, you need to remove multiples. To find an approximate image of an unrecorded primary, unrecorded multiples must be removed. Okay? So the very usage of multiples to get an approximate image of a primary requires another step of removing multiples that could be actually the unrecorded event. So, first, this assumes you have a multiple. How do you predict a multiple? You predict a multiple by having subevents, recorded subevents. You look for combinations. So to predict a multiple, I would need to have this and this both recorded. Okay? So if you have a multiple that you can predict, it's useless. Because if both pieces are in your data, the multiple has no use. It only has a use if one of its subevents is unrecorded. If one of the pieces is unrecorded, you can see that this is a multiple. Okay? It looks for combinations in your data. So a multiple is only useful if it has a recorded subevent that corresponds to an unrecorded primary. So if a multiple is predictable, it has no use. If a multiple is useful, it cannot be predicted. Okay? So this is well understood with the practitioners, and they have some, rather than predict multiples, which you can't predict a multiple that has a piece that's unrecorded, so they use all the data. And within all the data will be multiples. And the other parts will be multiples that have one subevent recorded and another not recorded. So, and all the other events are going to give you, they call it crosstalk, meaning artifacts, okay? Nevertheless, so the point is, the use of multiples requires another step. The use of multiples to go after an approximate image of an unrecorded primary requires you then to seek to remove unrecorded multiples. In other words, my statement earlier in this talk is every method that went to make a use, and a use which is worthwhile, didn't remove the need for multiple removal, it heightened it. There became an issue within the procedure itself that drew another need for multiple removal. We've said all this. Okay, here's another issue. Illumination. We often hear now, and there's a lot of mimicking, once one university says something, they all seem to echo whatever the fashion or flavor of the moment is. We need multiples because of illumination. It enhances our illumination, that we have illumination issues. Well, the response to that is John Claerbout said famously years ago that waves don't have illumination issue. Seismic data don't have illumination. They're ubiquitous. Okay? Waves don't decide which part of a salt they're going to enter. They enter the salt. Seismic processing methods produce illumination issues. Why? Because if they have a high frequency component, they have ray theory concepts in them. And rays take waves and squeeze them into rays. And rays, so a response is, if you're doing RTM and you have illumination issues with primaries, consider Claerbout 3 with the extension for heterogeneous media, because there's no high frequency approximation in Claerbout 3, the imaging condition, or how we've extended it in the propagation model. So you have not, in your processing method, in your imaging, have not introduced a channeling of this wave, yes, which leads to illumination issues. So can multiples be useful for that? It would have to go back to how you're going to use multiples to get an approximate image of an unrecorded primary. The point is, for primaries themselves, RTM is channeling, okay? That's what ray theory, in other words, you have a source and receiver above a reflector. Yes, that source goes off, that whole reflector feels that wave. Yes, and every point on that reflector then reflects back to that receiver. If I say this is what happened, that's a high frequency ray theory. So if you're using RTM, as we showed, its imaging condition itself is high frequency, yes? So when you're doing it, you're squeezing, in the processing, squeezing your wave. When you take it back into the earth, you're squeezing it, yes? Producing artificial illumination issues, okay? Just something to think about. We said this. Okay, let's look at indirect methods. So just to summarize, for direct methods, that we said, for methods that require a velocity, we understand why, as long as you have a smooth velocity in migration, or using multiples to get an approximate image of an unrecorded primary with a smooth velocity, yes? That multiples must be removed, recorded and unrecorded, yes. So, and if you have a direct method without a velocity, like ISS methods, inverse scattering series, the inverse scattering series says we have capability within us to, within ourselves, that you didn't make, you just looked at and found them. You didn't create them, they were there, yes? That capability to remove multiples is the inverse scattering series, which is the only direct method to do seismic processing directly and without any information to be known, estimated, or determined. In other words, when you finish removing multiples, you don't know anything about what generated those multiples. You didn't give it, you didn't estimate it, and you didn't produce it. The multiples are there and then they're not there. Okay? So so now we're moving to indirect methods. Indirect methods, there are different forms. One is to satisfy a property, like common image gather flatness. Yes, that's a property that you assume that an image would satisfy if you had the correct velocity. That property is for primaries. Okay? So that property itself assumes going in that multiples have been removed. Okay? The second type of indirect method is model matching. Okay? Model matching like FWI. Yes? By the way, common image gather flatness is indirect. What do you mean? It's a property. It's a necessary but not sufficient condition. You could have a common image gather as flat as a pancake and you're at the wrong depth, because the right velocity will satisfy it, but the wrong velocity can satisfy it too. We've seen that where we had common image gather flat and we drilled at Arco and it was nowhere in sight. It was somewhere else. So that's a condition matching. Okay. In general, are necessary but not sufficient. Okay. Hard to find a set of conditions that are sufficient. Model matching, where you match primaries, free surface multiples, and internal multiples in principle. Just match. In other words, you have a trace, actual. You have a trace from a model which has primaries and multiples. You adjust the model trying to make these two traces the same. Okay? That's what it's about. Okay? You can make it very abstract, but that's basically what it is. Okay? You can make it, fancy it up. You could put a different set of clothes on it. But what I just said is what it is. Okay? So, in practice, primaries are considered not enough. And primaries in all multiples are considered too much. Internal multiples are first removed, and then primaries and free surface multiples are matched. Why? There's no theory. Just, I can do model matching with one event. And say, let me try to match that event with primaries and multiples. And you say, why? I could say, why not? There's no theory, you understand? Match whatever you want. So, that again is not a bad thing. And as I said earlier, indirect methods, in my view, have a place, a role. Yes, it's the individuals who overstate capability. FWI never said, "I'm the last word on finding information about the Earth." You'll never find. I never heard FWI speak. It doesn't have an ego. It doesn't have ambition. It doesn't have a lack of integrity. Okay. The method is a method, and it has a place within the toolbox of usefulness. The issue is not the method or methods. And same with other, including methods in multiple removal. But here's the bottom line. In a recent workshop on FWI and velocity analysis, very recent, I gave the closing talk. The overall conclusion was that there was advance in FWI in finding information, in particular migration velocity information, but always an improved smooth velocity. And as we said, if you have a smooth velocity and you're migrating primaries and multiples, every multiple will give you an artifact. So after you're finished matching primaries and every form of multiples you want, if what your output is a smooth velocity, at the end of that story, you got to remove multiples to do imaging with that velocity. So FWI, in its current state of capability, we don't know. I think it's it's a stretch to say they will ever give an accurate discontinuous velocity, okay? Which is, by the way, what you need to do amplitude analysis at depth. You need the velocity. If you're looking for structure, smooth will get you a location. But if you want amplitude analysis, you've got to have the amplitude of that experiment at depth, okay? That means you have to have brought the wave through the medium. That's a very tall order beyond capability today, if ever, okay? So what this says is, either initially or ultimately, all multiples must be removed in all indirect seismic methods, okay? FWI uses multiples, but when you finish, you have a velocity that requires, when you image with that velocity, multiples need to be removed first, okay? So we're just, we summarized this already. So the bottom line is, what this talk has hopefully communicated to you is that all current seismic processing methods, direct methods that require a velocity, whether for imaging or to seek an approximate image of an unrecorded primary, yes, they will produce artifacts from multiples when you use a smooth velocity, okay, period. So that's why all imaging right now, unless you move to an accurate discontinuous and use a C3 imaging, if you use RTM with discontinuous, you're not going to deal with primaries through the one reflector, okay? And, but if you use an appropriate migration that can accommodate a discontinuous medium that derives from C3 and a continuous and a accurate discontinuous velocity, then multiples will never corrupt the image, never, okay? But we don't have that discontinuous, so multiples have to be removed. Okay, so hence, all direct and indirect seismic processing methods require all multiples to be removed either initially or eventually. So I want to thank you for sitting through this long talk, okay? The conclusion is here that the use of multiples does not in any way make multiples an equal citizen, you know, sort of a more inclusive world with primaries, okay? They remain an issue, a high priority issue, and as I've said, some of these methods which are indirect actually increase our need for multiple removal. How am I going to remove an unrecorded multiple? The use of, you understand? In other words, a new issue for multiple removal has come up with the usage. So again, I thank you for sitting through this long talk. The second talk, okay, which will be a separate link, will talk what is the current status of multiple removal, now that we hopefully have communicated why that's an important and pressing matter. On land, multiple removal is far from a solved problem. Our objective is to increase options in the toolbox. Now, as we'll say in the next talk, just because a method is more effective doesn't mean it's the method of choice. You need to have a cost-effective method. Yes, a method that can be less capable could be adequate for a certain circumstance. That's why we need to understand the assumptions of every method, so we know when to choose it under a given circumstance. Radon can be the appropriate method if you have a velocity and move-out differences, one-dimensional Earth. So, and it's much cheaper than any of the prediction of multiples with phase and amplitude. The problem is, going back to the old theme, when radon came out, it was sold as the last word on multiples. The answer, the news is there is no last word on multiples. Okay, there are open issues and challenges that require new thinking. And we need to avoid lockstep and encourage new thinking that recognizes the current capability, see what within current capability is missing, identify that. First, look at in detail what is currently available. Look at what's missing. What conditions, circumstances is the collective capability unable to address? Once though that is identified, then you look for methods that will fill that gap, that will add new capability. Don't find a method, put a French name or a Russian name on it, and then say, now after we have it, let's figure out why it's useful by ignoring or misrepresenting methods that are there. That is an unfortunate approach, and again, there are people who do that and there are people who don't. So again, let me thank you again for this talk. If you connect to the next link, you'll see presentation 2, which discusses how do we get multiples out, what's the current status. Okay, thank you.